Well, I hope you want to keep going through chapter 2, because if you don't, you're in the wrong place. So we're going into section 2.4, which is called Library of Functions. The objectives are just to be able to graph any functions in a sort of specific list, which the book calls a library of functions, and also analyze functions that are called piecewise defined. Okay, so we'll just start off with, here's a function root x. So its properties are, its domain is non-negative numbers. Okay, you're taking the square root, you better not be plugging in a negative. The x-intercept is 0, the square root of 0 is 0. Excuse me, the y-intercept is 0 also. It's not even nor is it odd, which you should be able to verify. It's always increasing, and it has an absolute minimum at the origin. Okay. All right, so I'll give a quick sketch of it. So the graph of root x, its domain is x is bigger than or equal to 0. The intercept is right here. It's neither even nor odd. It's always increasing, and it has a minimum right here, but it doesn't have a maximum. Okay. So can you graph the cube root of x, determine whether it's even, odd, or neither? Does it have any symmetries? Find the intercepts, if there are any, and graph it. So you should be able to verify that it is actually an odd function. The cube root does actually distribute. This is because negative 1 cubed is negative 1. So the cube root of negative 1 is also negative 1, which means that the cube root of negative x can be expressed as the cube root of negative 1 times the cube root of x, which is negative 1 times the cube root of x. Okay, so it is an odd function. So it does have symmetry around the origin. The cube root of 0 is 0, which is the y-intercept. It's also the x-intercept. Okay, it's the only place that f of x can equal 0. So the origin is both the only x and only y-intercept. Can we graph it? Well, because there's symmetry around the origin, okay, if I can just figure out what happens for positive x's, then it will just get symmetry around the origin put to be what happens for negative x's. So we really only have to do positive x's, which also gives us positive y's. Okay. If we plot out a kind of table of some cube roots of values, we get the cube root of an eighth is a half, the cube root of 1 is 1, the cube root of 8 is 2. This gives us some values here, and then we can just reflect them through the origin, because we already know the function is odd. So here's a graph of cube root of x. Okay, so what are some properties of the cube root function? Well, from the picture we just saw, which I'll just sort of resketch, the domain is all real numbers. Okay, the range is also all real numbers. The only intercept is at the origin. It's an odd function that is always increasing. Okay, this is always going up, but it does not have any local maxes or mins. Okay, let's take a look at the absolute value function. Is it even? Is it odd? Neither or both. Find intercepts and graph it. Okay, so pause for a minute to determine whether it's even or odd and what its intercepts are. Okay, it is an even function, so it's symmetric across the y-axis. The absolute value sign allows you to ignore that negative. The only intercept is the origin again. Okay, and the graph, again, because it has this symmetry, it's going to have a symmetry across the y-axis. So if I can figure out what happens for positive x's, it will automatically tell me what happens for negative x's. So for positive x's, we get this line, and then I symmetrically reflect it that way, and there's our graph of the absolute value function. Okay. So what were the properties? And again, I'm just going to resketch that graph down here. I didn't draw particularly well, but there it is. It is defined everywhere. The intercept is here at the origin. It is decreasing here and increasing there. It's an even function, and it has an absolute minimum there at the origin. It does not have any maximums. Okay, so some key functions to remember. Constant functions are just horizontal lines. Y equals x, also called the identity function, is a line of slope 1 going through the origin. The x squared function has the following graph. That upward opening, the shape is called a parabola. Okay. Also, the cube function has this graph. Square root function, cube root function, we just discussed. The function y equals 1 over x. If you plot out some points, first of all, you'll determine it does have symmetry. It is an odd function. So if I can just figure out what happens for positive x's, it will tell me what happens for negative x's. Get a shape like this, which reflects across the origin to be a shape like this. This function, where is it increasing and decreasing? It's always decreasing, actually. If you're moving from left to right, you're always getting smaller everywhere on this graph, which is kind of interesting. But it does not have any maxes or mins. The absolute value function we discussed earlier. Okay. The greatest integer function is a curious little function. We're not going to discuss a whole lot in this class, but it's used a lot in practical purposes. This is basically rounding down. So what is the greatest integer rounded down part of, say, 3.8? 3. What's the rounded down form of 1.6? Whoops, go back. Of 1.6? 1. What's 2.0 rounded down? Hey, it's 2. Now here's where people get it wrong a lot. Whoops. What is, say, negative 3.8 rounded down? It's negative 4. A lot of people would say, oh, negative 3. But negative 3 is bigger than negative 3.8. That's rounding it up. So the greatest integer function always rounds down. So negative 3.8 would round down to negative 4. Okay. And so if you tried to graph this, it's kind of curious because everything from, say, 0 to 1 rounds down to 0. But as soon as you hit 1, everything from 1 to 2 rounds down to 1. Everything from 2 to 3 rounds down to 2. So the graph is this sort of sequence of steps that include the point on the left but don't include the point on the right. As I said, this isn't a function we're really going to use very much, but it is a curious one. Okay, now a piecewise defined function is a function where it's defined one way if x is a certain thing and defined a different way if x is something else. So in this example, if you plug in a value less than 1, you compute this. But if you plug in a value bigger than or equal to 1, you compute this. So let's find f of some specific values, ask what's the domain, locate intercepts, and graph it, and find the range. Okay. So try to work through these 5 little subproblems. I'll pause for a second, and then I'll start going. All right, hopefully you actually did it and did what you could. So if you plug in f of 0. So the function was defined. I'm going to flip back to the other slide so we can see the definition. If you plug in something less than 1, you do a certain computation. Bigger than or equal to 1, you do another. So if I'm plugging in f of 0, I need to compute this, because less than 1. If I plug in 2, well, that's bigger than 1, so I would compute this. If I plug in 1, that's bigger than or equal to 1, so I would also compute this. So since I'm plugging in x equals 0, I compute this part here, which just gives me 1. But if I'm plugging in f of 1, I need to switch over to the other part, and that's going to give me negative 1. And similarly, if I compute f of 2, I'm doing that second computation, and that's going to give me negative 3. Now the domain for the first part, I can compute whenever x is less than 1. And then the second part, I can compute whenever x is bigger than or equal to 1. Overall, there's actually no problem. I can compute f for any real number. So the domain is all real numbers. Some y-intercepts, okay? The easy one is the y-intercept. If I set x equal to 0, I know I compute according to that first computation, and we've already done this f of 0 is 1. The x-intercept is a little tricky, okay? I want to get out y is 0. But there were 2 parts to the function, and each one of them might be equal to 0. So maybe x is less than 1, in which case this function would have to be 0. This is how I compute the function when x is less than 1. So if I solve this for x, I get negative 3/2. Is that actually less than 1? Yes, it is, so this is fine. Okay. The other branch is computed like this. If x is bigger than 1, I compute the following. And that solves to x equals 1/2. Okay, but is that part of this function? No. If x is 1/2, I wouldn't have computed this, because x is 1/2 would have computed this branch over here. Okay. So we actually discard that, okay, because that computation was based on the condition that x had to be bigger than or equal to 1, so 1/2 isn't a legit input there. Okay. So x equals -3/2, that worked, because that was less than 1, and that was the condition. So that is an x-intercept, and it's the only one. Next, can we graph this? Well, we graph each equation just stopping where that cutoff is. Okay, so we graph one line, but stop when x, but we only include the part to the left of 1. And then we'll graph the other line starting at 1 and going on. And we get the following picture. Okay. They happen to meet up at this point here. A piecewise defined function doesn't have to. We could have had something that looked like this. They may have just had a gap there. These two functions happened to meet up at the point in the middle, but it doesn't have to. Okay. So from the range, notice this is increasing all the way until I hit this, and then I am decreasing away from that. So the biggest value I ever reach is 1, but I'm going to keep going down to the left and to the right so I can go off to -infinity. All right, next example. I'm going to go ahead and stop this video here just to, in the interest of time. But we'll come back and we'll do this example.